that's what I'm going to do since that's our product. I'm going to talk about a lot of things, a lot of the ideas that led into the development of React, but they're not specific to that. I'm going to try to talk about things that are valuable to everybody building distributed systems. And so when I talk about concurrency at scale, right, and scale is why we're all here at church, right? Scaling up, scaling out, whatever. But it really means distributed systems. And the fundamental problem in distributed systems is concurrency. And that's really a problem about time. And so most of what I talk about today, I'm going to jump around between subjects, but it's all really going to be about time. And why you need to care about actually thinking about concurrency when you're building distributed systems. And this is not a, parallel programming, this time is here, the free lunch is over kind of a talk. It's not that. This is much more about, we're now building systems that have to be made of multiple pieces talking to each other to do our job. And there are some ways that we have to think differently to make that work. And, there's a bunch of kinds of systems that we're building that have this property. Obviously distributed data storage systems, I'll mention React, right? Those are dear to me. But there's lots of other things, right? Some people are trying to build reliable systems out of many unreliable components. And, there you fundamentally are dealing with concurrent behavior of lots of different things going on. But in general, almost everybody who's here because they're interested in figuring out how to talk about scale in some meaningful way is talking about a concurrent system. These are problems for all of us. But the thing is, we're putting more and more on the web, and sure, it's still not at the level that John was talking about. We still don't usually have people dying when we screw this up. But people are caring a lot more on a daily basis about these systems on the web actually working and depending on them. Things like, our bank accounts and things like that. And so people are expecting much more dependability at the same time that they're expecting us to handle so many more kinds of behavior. And the thing I really want to point out is another way of talking about time here is that much like John and Brian and Theo are all saying, let's pay attention to academia, let's pay attention to history, right? Because a lot of the problems that are coming up as people are building these concurrent systems, we can actually learn from what people have already done that largely gets ignored in a lot of work on the web. Or gets, tossed aside as, well, that's academic work over there. And sure, academia might not be serving us perfectly, but if we're going to make that work better, we need to figure out what we can learn, what we can remember from the past, and it's not all in computing. But I put concurrency in the title, and if I use a word that much, I tend to want to make sure that we both mean the same thing by the word. Especially when it's a really tricky word. It can mean more than one thing, right? You can mean concurrent, right? Things happen at the same time, parallelism, simple things. And that's a valid meaning of concurrency. But it's far more interesting. And we do it every day in conversation, talk about a different type of concurrency. If I say that I concur with some of the things Theo just said, I'm saying that I agree with those things right now. And both of those parts matter, the agreeing and the right now. And that's where this becomes a really hard problem. And that's where this becomes a more subtle problem of time, right? Existing at the same time as you is easy. I don't have to have any communication with you for that. That's simple concurrency. Believing the same thing you do at the same time you do is nearly impossible. And all I can really do is agree with something he said 10 minutes ago. He may have changed his mind since then. And this might sound like I'm, just sort of going on in general in vague terms, but that's because this is a big, hard problem. It's not just about computers, right? I mean, for instance, starting in roughly the 30s, the 1930s, a number of people were figuring out in physics, this is pre-computer science here, that time is a much harder problem to work with than a lot of us like to think. And we often design our systems, our new modern web systems, and think personally as though time is a happen at the same time. And it's really a lot more complicated than that. And we don't actually get to know what's happening at the same time to anybody but ourselves. All we get to know about is the past. And people have worked really hard on these problems, not to make them simple. They've figured out that's impossible, but to figure out what reasoning you can do about causality, about knowing what you can believe about what someone said before. And, you know, we've started, still old history from a computing's point of view, to actually know how to reason about these sorts of things in computing. Right? It's been since the 1970s that Leslie Lamborn introduced the ideas of logical time as a computing. And the way to ask, how can I tell if something happened before something else? And sometimes you can't tell. And, you know, about 10 years later, Friedman and Mattern came up with a structure that's been referred to already once today, vector clocks. Which the neat thing is the way some people draw those here. Actually, if you turn it on its side and I go back a slide, it looks a lot like those scalability terms that are the way of physicists might have fun sketching things. Because it's the same idea. And because in computing, we also have to think about time not as a single linear flow of events that everybody gets to move in lockstep. That doesn't actually work. It's a hard problem. We like to pretend it's easy because we get to make up our own abstractions. You know, we want to write programs that feel right, that feel simple to us. And a lot of us have developed an intuitive sense of time as just being a single linear flow. But what I'm going to talk about is the fact that when you think that way, you write worse programs. Things will break. Because we're talking about scaling our systems. We're talking about distributed computing. And the point here is that distributed computing is fundamentally asynchronous computing. And you know, I would go even farther than some of the things Brian said an hour or so ago about how we need to build asynchronous systems to do all this sort of thing. We're doing it already, and sometimes we're hiding from it. Distributed systems are asynchronous systems. Always. It's not the other way around. It's not that we build asynchronous systems so that we can get distributed. It's that once you have more than two pieces talking to each other, you do have asynchronous. They do not have the same idea of truth at any given moment. Now, we do lots of things, like distributed transactions, to let us pretend that we're acting at the same time as each other. And sometimes we need to do that. Sometimes that's the right choice. But every time we do that, for some amount of time, some space in our system, we're throwing away a lot of the reasons to build a distributed system. Because what we're doing is we're deciding to pretend for a minute that there's such a thing as global state, right? That's what distributed transactions are all about. It's all about some set of parties all thinking that the state of the world, the database or something like that, is the same information for all of our parties. It's not true, right? You can pretend by having everybody do nothing while somebody else acts, and that's really what distributed transactions end up boiling down to. But if you want to really take advantage of the fact that you have a distributed system, you have to start out by acknowledging there's no such thing as global state. Every time you pretend that there is, you're going to either break things or lose a lot of the performance and availability reasons why you built that distributed system in the first place. And you're going to reason wrong about your systems. And I don't want to talk too hard about really reasoning about systems here, but I am actually going to briefly, to make a point about how bad it is to think in terms of global state, make a digression into another field to talk about the real scary problems of thinking there's such a thing as global state. I'm going to talk about cryptographic protocols for a moment. Don't worry about the notation. This is a key exchange protocol. Key exchange protocol has been around for a very long time. It was invented by Nina Schroeder. It's a way of using public key cryptography to establish a session key. The only reason I put this up here is to make a point that when this protocol is written, this is often the kind of notation people would use to represent this sort of thing. And it has implicitly in it the idea of global state, right? That there's one message there that A and B both interacted with. That there's a global reasoning that I can do about my data. And people thought that way about crypto protocols. That's how people built them, and this was thought to be pretty good. Until more recently, people thought more about the fact that we don't really run our protocols this way, right? We run it with a whole bunch of potentially either broken or evil stuff in between those parts. Right? Who knows what? The internet, all sorts of components that can of great logic for crypto that you can do to figure out what you know, and it turns out that a couple of the things in that protocol you don't actually get to assume anymore when you switch to local reasoning. And that can lead to some very bad things happening. And the point I'm making is that the guys that Needham and Schroeder that invented that first protocol, brilliant cryptographers. And that was an incredibly well-known protocol for 16 or 17 years before Gavin came along and broke it. Because our tendency is to think in terms of global state. When we do it, we're wrong. And we make systems that are broken. Not just slower, broken. Any given party only ever knows about the past. It knows what it's heard, but it doesn't know what someone else thinks is true. And now to get a little bit more concrete and talk about some of the things that seem to be a developing theme this morning. What that means is, in a working distributed system, you actually have to take advantage of that system, very often give up on those acid properties that we've talked about a little bit already. And I'm not going to beat the drum and say there's a right choice here. I'm going to say that sometimes you have to, in order to actually make a meaningful distributed system, give up on those properties. And so I'm going to say why you have to. Right? We talked a little bit about the trade-off, but the point here is to say how this concurrency matters. Because, as Theo was pointing out, a lot of these definitions get thrown around without actually understanding why we care about these different terms. But as soon as you acknowledge that there's no such thing as global state, and that all I know about is the past, you immediately lose the fundamental, atomic, isolated way of thinking about things that happen. Because if I send you a request to do something, unless we're in some distributed transaction where everybody promises to do nothing until they hear back later, and sometimes you can do that, but I'm talking about a distributed system that actually wants to do work. You just lose those properties right away from the get-go. And similarly, when you do that, you get to the beginning of base here, right? You trade those off exactly so that you can build a system that's available instead of having everybody halt at once to wait for things to happen. You give up those first properties for a reason. And similarly, I send something across the network, and unless everybody halts and does a global two-phase commit, I don't know about durability. But that's where we get soft state. I know what I can believe I've asked others to do and what they've told me to do. And then, of course, we get to the scary part, right, where we give up the traditional part of consistency, and we talk about eventual consistency. And the history was actually backward in one of the earlier talks. It was actually that Eric Brewer said this, and then a couple years later, trying to rephrase it as the cap theorem is actually make it easier to understand. And it was a great effort, but I don't think it worked because it generally isn't understood. But the point is that this is a real trade-off, right? This isn't this one wins. And it isn't that, that there's a series of things coming along that are new, acid, and base, and dirt, and so on, right? It's that these are ways of thinking about the systems you're building that you need to know what trade-offs you're making. And so, since I'm claiming that the cap theorem is mostly misunderstood, Theo claims the same thing, but I want to actually help make it understood a little bit, because I do know what the definitions of those words are, and they're not that hard. When we talk about consistency in terms of the cap theorem, we're talking about the C in acid, which is a simple serializable consistency, which you can really think of it as meaning there's only one state. That all the parties in a system believe the same thing at all times. And that's exactly that property that we said we have to give up in distributed systems. Not just when we want to make our database more available and all that, but there is no such thing in a real distributed system unless everybody halts. Availability, really in this context, meant that if you can reach any functioning host in the distributed system in question, that one will act on your behalf. That one will work. It will be able to take action. And partition tolerance is about the fact that no matter what sorts of network problems you maybe have, arbitrary, even maliciously designed packet loss, the parts of the system you can reach will continue to function. And the trade-off is simple, but it's also not about picking two, right? The oversimplification is you've got three, you pick two. It doesn't work that way. What it means is, this is not about how you build a system to work. This is how you build a system for when it's failing. CAP is about what happens to a given system when it's broken. they're broken. And so you don't give up all bits. You want to have all bits. Which ones do you bend when you have to bend one because you have no choice? And so the traditional distributed transactions that I've been making fun of bend partition tokens. Except that's the only one you don't really get to bend. Guess what? Your network fails some of the time. You do have packet loss. You don't actually have a perfect connected network. You're not just the internet. Anybody here who's actually been operating real systems, your local switch with all your machines on it isn't working right all the time. So if you have a system that says it's a CA system, no, it's not. Because that's the one that actually you don't get any real control over, because I don't know any network that anybody built, even the really expensive ones, that gets to claim that that's the thing it can give up. Because otherwise it's just not there. And you give away the rest of the game too. You give availability at the same time. So you get consistency because you can't talk to your computer. It's very consistent. It tells you nothing. Another trade-off you can make, which is a little simpler to deal with in certain failure scenarios, is things like forum protocols, where you give up availability and you say, if my machines, some of them are down, some of them are unreachable, I'm getting some of that network behavior, maybe not all the parties can work. And if I reach someone in a minority or that's not currently, it doesn't work. That's a perfectly useful trade-off for lots of situations. But of course, the trade-off that gets all the attention lately, the NoSQL and all these other things, is consistency. But this is just about saying, well, I know the network's going to have partitions, and I'm being judged on availability. That's what my users are going to talk about most tomorrow. And so sometimes it's okay to be a little stale, to be not stale in the business person's point of view, but serve something up to the second old, right? That's all that we're talking about here, is allowing yourself to continue under load, under failure, sometimes by having two different parties on the network disagree about what they're saying. And so this is just a natural outcome, this particular compromise, of the base ideas. And again, it's a trade-off. There isn't a right choice there. There are right choices for different scenarios, and if you're building a big, interesting system, you're not going to make the same trade-off all the time. Not only are you going to use different databases, you're going to use them differently, your applications, you're going to use them differently. But I do want to talk again a bit about eventual consistency, especially since I really disagree with something Theo said a minute ago. Because I think every day, financial transactions, purchases, things like that are happening in an eventually consistent way. And it's fine. Because our computers are producing a model of part of the world, right, that we're interacting with. I might be trying to buy, a book online, and I bought that book, and I might say, well, I really want to make sure that, my credit card's charged, there's perfect consistency, and I get that thing shipped. And you might say, well, I've got a book left in my inventory, and he's got the money in his credit card, I can go ahead and do it. But you don't know that your warehouse is on fire right now, because your system didn't include that. Your system's eventually consistent anyway. It's eventually consistent with the world, because there's no such thing as global state. Even if you slow down your system enough to have good enough internal pretending that you have global state. You might, in fact, accept a transfer from a bank that's insolvent. You might ship a book when the warehouse is burning down. You don't get to have perfect consistency. So, we're giving this up all the time on important transactions. And this is how banking has worked since way before there were computers. Right? This is what double entry accounting is. Right? We'll take records. We'll do accounts. I'll take a deposit. I don't pretend to be providing a consistent single global value all the time if I'm an accountant. At the end of the day, I balance the books. I might do it sooner if someone needs to audit. But we're talking about the most important transactions people do. They're already being done that way before we were programmed about them. Pretending that we can do better inside our web systems won't work. And I'd also argue that this is not in conflict with some of the real-time ideas that we're just coming up. Because this isn't about being slow. This isn't about saying, I'll eventually get you the data. It's about saying there are times when it's okay, in a measurable, planned way, for some parties to believe something other than someone else for a limited amount of time. Now, that amount of time is exactly your real-time constraints on your system, right? So if you have a hard real-time system that has real constraints, 350 microseconds, then you know exactly how long you have to manage the eventual consistency in your system. For instance, the time between when you actually get a signal over that thing's radio antenna and when you act on it, there's eventual consistency there. Not all of that actuator knows that information when it hits the radio. So eventual consistency doesn't mean slower. It just means that you're acknowledging the fact that the entire world, including the computers we're writing programs on, is asynchronous and has no such thing as global shared state. It doesn't exist. We're all eventually consistent. It's taking you a very, very small fraction of a second after I say this to hear. Physically, the world is eventually consistent. You don't get to escape that, ever. So what can we do? What can we do to make our systems feel safe enough? One of the things we can do is instead of talking about moving the big, giant global state around, talk about what we like to do. Just like in accountant's books, you don't write down the new balance every time. You write down the changes you're making. And so by thinking in terms of operations that different parties would like to make, you can get a little better. And there's some principles you can use to make managing eventual consistency over those operations much easier. And neatly, I'm not the first person to do this, you can make a convenient acronym out of some of those properties you'd like to have. It's not the S that you might be used to thinking of. But if you ship around operations, like for instance, instead of change the number in my inventory from 2 to 1, you can say something like, well, hey, this is machine X, I'm going to issue, request number 42, reduce the count by 1. That's a very different thing to send than change the value to 2. Because that sort of thing is arithmetic. So it's associative and commutative. There's lots of things you can actually make out of those properties if you try it. And the whole reason that I said, and this is request 42, is so it can be identical. You just want things to be replayable, because you're going to lose networks over time. And so I don't want to subtract it twice. And there are well-known ways to make us not have that sort of problem. They're easy. You just have to actually decide to do them. And that's how we get to have these systems be distributed. So I'm going to get a bit more concrete and talk about some things that I think don't work and do work. But before that, I want to talk about why I've given this more abstract background. Which is really, this is all about time. We're talking about scalability, we're talking about distributed systems. These are time problems. We are building asynchronous systems. Own that fact if you're trying to make those systems be available. Because when you try to make them pretend like everything's synchronous, you take away much of the value both for capacity and for availability of building such a system. And, so throwing away these notions of global state is necessary in these kinds of situations. But that's hard, right? We like to think that way because it's really easy. And so I've now said, these are bad ways of thinking, so what do we do instead? And so now I'm going to say something worse. Instead of just saying don't think that way, I'm going to take away a piece of your toolbox, in order to give you helpful advice. Because here's a really bad idea. Remote procedure calls. Concrete something that doesn't work. This is something that's asked for here, more stories, right? The remote procedure call is used all over the place in building distributed systems. It's one of the most fundamentally bad ideas that we've got in computers. It takes an abstraction that we know how to reason about, the function call. Something we know how to describe how it behaves on a machine, we know how to reason about it mathematically, and it throws a network under the hood. And it's not that you can't make that work sometimes. I've done it. I might even do it again sometime. But it introduces all kinds of interesting problems, right? When I make a function call, I generally know that there's a set of things that could happen. If I make a function call and it happens to be an RPC, the other end of that call might succeed, and then the network might fail all the way back to me. This kind of thing happens all the time. And we have no way of thinking about composing functions in a program to describe what happens when my function succeeds, but couldn't tell me that. Right? That's not a normal exception. Right? Exception might say you failed, but if it doesn't know whether the function happens or not, it doesn't work. Right? You don't know how to write programs like that. I don't, and I've tried. You may have tried. I'm willing to bet you weren't reasoning about that fact in there. And there's all these things that make RPC really different from regular procedure calls. And one of the worst ones is that most of us do our development locally, on your laptop or whatever. And it'll work great there. Because there's no real network, right? You're faking yourself out. And then once you deploy, behavior is utterly different because it's not just the time. It's the semantics of your function calls have changed. They now mean go talk to somebody. And so, this is a mess. I built a system on this a long time ago and seen that RPC-based systems over time, initially you might be able to do it okay. Over time, through maintenance, through multiple programmers, you compose things just like you do another program. You refactor things, you move your functions around. And sooner or later you have an RPC that calls some other function, calls some other library, calls another RPC. And things start to get harder, and things start to break. And I'm going to argue that if you do this, at least know that you're introducing a fundamental fragility by mixing up two abstractions that don't mix. So, the problem is they're really handy, right? It's really nice to write a program in terms of function calls. We know how they work, except these don't work. So what do you do instead? Well, we talked about protocols before, and I'm going to say that's how you do this. In an asynchronous world, it's all about messaging, right? You throw messages around different parties, you describe what those messages mean, and you can actually build systems where you understand how they work. You can know where failures could happen. You can know where, if one of your systems is hacked, what effect that can have on the other systems you're running. And I would argue, even though this might not seem it immediately, that you also have much better composability, right? It feels like you have better composability when you're using a function call like abstraction, but you don't know what you're composing. With protocols, you can actually reason about it. And they let you think about the fact that you don't have shared state. About I know something, I have to tell someone. Not we all get to pretend because it's all of these function arguments. And that reasoning, which, Clojure and Erlang has libraries that actually help people do, lets you build distributed systems that you can think about, that you can add new pieces to without breaking things. That's huge. And I'm not telling you to go use these. I'm saying there's some examples of people that have actually solved this in real programs doing real things. But most of us, most of the time, aren't doing that. But when I'm talking about protocols right now, I'm not just talking about, the more obscure programming languages or arcane crypto protocols. This matters in the protocols you use today. Right? Again, Theo was talking about DNS and HTTP. And those are protocols every single person in this room cares about every day. They're part of why we're able to do our jobs. Many of us know some of the words in each. They're not perfect, that's not the interesting thing, but guess what? They're both fundamentally designed around the base ideas. So, like for instance, in DNS, if I make a change on my root DNS server of whatever my domain is, I don't expect that you all see that right away. Right? Nobody does. We've absorbed that, right? We've all internalized that how DNS works and become okay with it. That's just eventual consistency, right? We have TTLs. We know that there's this cascading acceptance of data. It's just eventual consistency. You're using it every time you do a name on that. Similarly with HTTP, where you can specify an expire set that lets that page sit around for a second on your varnish or squid or what have you. That's eventual consistency. That behavior is fundamentally part of these protocols. And that's why these protocols were so key to successfully building what I would argue is the most important to all of us and most successful distributed system out there. And that's the World Wide Web. I don't mean your web server. That's not the most important thing. The most important thing is the web here. It's a distributed system. Right? By any meaningful definition, the web as a whole is an enormous and incredibly successful, very available distributed system. And how is that able to work? Well, guess what? We acknowledge there's no global state. The closest thing we have is, we don't change how often we talk to the DNS root servers. There's some mind things. That's not really interesting. That stuff changes on months or years scale. And we have all these caching things. We have eventual consistency. We have loose coupling. We don't have global relations. There's no huge database table in the sky that runs the web. That wouldn't work. I think everybody knows that wouldn't work. It's a distributed system with no global shared state, with an asynchronous set of protocols that have eventual consistency. And that has allowed the web to scale way beyond its initial expectations. And so how have we been able to do that? Right? Let's take our trivial tiered architecture here. here, right? The simplest we can draw it, and the way everyone probably has at least once. Except that HTTP layer, we were just talking about how great that protocol was. Well, it's true, that let us easily scale out that aspect of the web, right? Because that protocol has all those fantastic features that let us build things like Akamai, right? And that's actually the first real-world use of consistent hashing that I know of, about 10 years before Dynamo, for content location in a lot of the same ways, like around the world instead of in a data center. And that made it pretty easy, conceptually, to scale up that part of the web and get a lot more connections, because we've got these protocols that you can talk about that. Since then, over the past 10 years or so, people have gotten a little bit better at figuring out how to make their own applications that they write to have some of that same behavior. The asynchronous and communication across servers, all this sort of things. We've gotten better at that. A lot of the way we've gotten better at that is by pushing the problem down into our database, right? We make our applications be stateless by putting all the state in one other place. And that one's scary, right? You know, we can talk about, NoSQL and what to use, what not to use, but the real thing is this is the one we're worst at right now. Because it's the one that's hard, right? This is the one that's all about the state we care about. And there's a lot of work going into how to better make our databases scale up, scale out, and do all these sorts of things. But if we're going to talk about scaling this much, I want to talk about what the word means, because I don't think everyone uses that the same. Because, hey, it's web scale, right? Is it fast? Is it big? I don't know. A lot of the time, scalable gets used as, just a positive adjective about systems that go, right? It can mean big, it can mean fast. And it doesn't mean those things at all. Something can be really scalable and, handle one request a second slowly, right? It doesn't mean that. It's about a trade-off. It's about cost and benefit. And if you're going to talk about how do you build scalable systems, you've got to know what the heck you're talking about in that trade-off. And so you've got to have some sentence of roughly this form that makes sense to have something scalable, right? I can add more of something to get more of something else. That's what scalable is. It's the ratio between what you have to pay and what you get in exchange. And usually, a lot of us like to talk about, scaling out, so scaling up. The same thing applies, right? If we're talking about scaling up, X might be, RAM, faster CPU, etc. If we're talking about scaling out, we might talk about computers, right? If I add more computers, I can do more. What can I do more of? It doesn't matter. Maybe I can write more data. Maybe I can store more data. Maybe I can compute more. The point is, you got to know how to fill them in. If you don't know what words to drop in for those variables, and you're telling me you have a scalable system, you don't know what you're talking about. Fill it in. Write the sentence. Talk about scalability in terms that someone can actually learn something from. And I structured the sentence actually in terms of the kind of scalability we like to talk about. When I said that twice and twice, I put a nice simple relationship there. A lot of the time, we'll talk about linearly scalable things. That's just what shape that curve is in your cost benefit. You can be all different kinds of scalable. A lot of the time people assume you mean linear scalable, right? I can double to get double, I can double to get triple. It doesn't matter, that's a line. But thinking about scalability means thinking about cost. It's not thinking about how do I make it big, how do I make it fast. It's thinking about how can I make it so that there's a ratio that I understand of what I have to pay to get what I need. So the other thing we like to talk about a lot about the systems we're all building here is that they're reliable, right? They don't fail. They're up. When people go to get them, they work, right? They don't fail. Nothing except it will. Right? Everything fails. And it doesn't matter what you're doing. You have to assume that the components of what you built, the ones you built, the ones you bought, everything else is going to fail. It's going to fail in incredibly ugly ways. So I don't like to talk about reliable that way. I like to talk a little bit about resilience, which is about thinking about how you keep going when something's broken. And understanding what failure means to your larger system. And so then you can understand when you still get to have business success of your mission, despite failure of the things you built. Knowing how and when you cross different thresholds of failure. And there's a lot of work on this, right? But partial failure is important because something's broken all the time. And as we all talk about building scalable systems, you're adding more pieces, which means you're adding much more chance that at any given moment, some piece is broken. And you're having much more chance that the worst possible set of pieces are broken. Just know which ones of those cause which effects to your business. Do that analysis. You can do it. It's not that hard, but people don't do it that much. And it means that you don't know what you need to fix. And that leads to really scary behavior when things are broken. Sometimes things get a lot worse. I've seen that too. If you do this planning ahead of time, you understand which failures lead to which other failures. You can understand a lot more. And there's actually been a bunch of research on understanding partial failure. Some of that work, pre-acid and base, pre-cap, was on harvest and yield. And the idea here, I actually think this is simpler. The funny thing is, a lot of the base stuff and a lot of the cap stuff was supposed to help people understand this better. This is actually the easy one to understand, I think. Because it's really, really simple. If you're making some request in some distributed system, the harvest here is just how much of the current known state in my system did that request get to interact with? You know, how close am I to really having local state? And yield is how likely am I to actually satisfy each of those requests? And in any given system, at any moment, harvest and yield together are actually in tension. They yield a constant multiplied together. Pretty straightforward, which means that the more you push on one of them, the more the other one pushes back. And the reason this is worth talking about is we go back really briefly to the acid and base thing. What acid means, and the whole reason why we talk about this difference, is that acid means it's all harvest. Acid means you always sacrifice availability, yield. You always answer less requests in order to be more perfectly consistent. Which, you know, is a really laudable goal, except what's the thing you hear most about failures of everybody's web application? It's yield. It's how many requests they satisfied, whether they were up when you went to them. And it doesn't mean you should go 100% the other way. That's at least as stupid. It means know how your system behaves in terms of harvest and yield. Even better, know how to turn the dials yourself. If you can build a system where you get to change these things because of operational scenarios, right? I've had a system before where in operation, 3 of that system's 5 databases were suffering simultaneous failures. 2 of them were not going to get recovered that day. They were hardware failures that we weren't getting fixed that fast. So we changed some of the parameters, and we went for making some of that data available off the slave. It might have been stale, and all this. People make these kinds of decisions in operations. That's what you're supposed to do, right? That's a business decision. But if you haven't understood the trade-offs in your system about harvest and yield, then you don't know the impact of making those decisions on your users. And you can't plan. And you can't plan without measuring these things, right? You've got SLAs. Now, in some cases, they're explicit SLAs. They're part of the business contract. You owe someone money when you file it. If you're providing some website to somebody that's not part of the business, but it's some social network, something else, your SLA is really in terms of social capital, right? And it's still an SLA. There's expectations people have upon you for availability. And you don't know whether you're going to be able to make all of those parties relying on you happy, unless you're measuring yourself. And this isn't just to see, am I satisfied, right? And now analyze everything we've got, top to bottom, and correlate. This is something that I think some of the graphs that John was showing earlier, and that Theo showed actually, the more recent one, are exactly what we're talking about. Heck, all morning, Brian talked about t-shirts, right? If we can put measurements in your system to let you do things like correlate not only hardware behavior, operating system behavior, database behavior, application behavior, user action, right? All of these things, and across your distributed systems, that's when you start to understand the meaning of your actions. And of course, latency. You have to measure all these things about time too, right? And it just comes back. In the end, it's all about satisfying the problems of time. And if you don't acknowledge that time is at the core of all these, you're going to forget most of the things you need to do. And it becomes harder and harder to build a working distributed system. And speaking of time, I'd like to make sure that I can answer any questions or have any discussions that people want to have, and not be the thing that is in between people at lunch. Are these slides available online? They especially or not, but if not,